So let's have a look at the kinetic interpretation of temperature. Now, in my previous lectures, we had come to the conclusion that P equals to N, that is number, into M into Vx whole square into the average. This is the average. Now, this was for a unit dimension, that is for a single dimension. Now, we have assumed that Vx, if a component is flying, that is a component is traveling, so it has a Vx component. Similarly, it will have a Vy component, and similarly it has a Vz component. So if I generalize, I know Vx should be equal to Vy should be equal to Vz if for the whole system, if I want to generalize. So this in turn gives me this, which is equal to, if Vx equals to Vy equals to Vz, then we have 1 by 3 into Vx plus Vy plus Vz. This is square, square, square. This is the average. So this becomes 1 by 3 anyone, that is if Vx, Vy, Vz, we know V is equal to Vx plus Vy plus Vz. Now V is divided into this component, and we know Vx is equal to Vx plus Vy plus Vz. Therefore, V is equal to the velocity of the particle is equal to 3Vx. So if you want to find Vx in terms of V, you will have 1 by 3V. So this is the way how this is derived, and it is directly put into your formula. So now we have 3V, 1 by 3V whole square. So now my pressure in the wall becomes 1 by 3 nmv square. So this is what we have derived so far. Now if you want to interpret the kinetic, that is interpret the kinetic interpretation of temperature, what we have to do is we have to start from here, start from this equation. We know PV is actually equal to, put V over here, 1 by 3 V for volume, this is volume, into N into M into V whole square. So this is what we have derived from over here. Now moving on, say let's do this with different color. PV equals to 2 by 3. Let's take 2 common here. This is V volume into N. This is N. Now, if you observe closely, what we can do is, this is volume V and this is N. So what we can do is half. We have taken 2 over here, and this is half. This is small m. This is small m. mv square. Half mv square. Now if you look over here, half mv square is nothing but your kinetic energy. This is your kinetic energy. So in this way, by placing into a correct order, we can derive the relationship between the kinetic interpretation of temperature with energy, that is kinetic energy. So this is nothing but your kinetic energy. Now if you look closely over here, this is the total volume, and this is the number of moles, that is the number of molecules that is present in 1 unit volume. We are talking of number of molecules present in 1 unit volume. Number of molecules, or any number present in 1 unit volume. So if you multiply this with the total volume, if you are multiplying this with the total volume, you get the total number of molecules in the system. This is total number of molecules in the system. So now you can easily remove this n. That is, easily you can remove this n, because n equals to small n into v. Therefore, your equation becomes 2 by 3 n. This becomes 2 by 3 n into half mv square. And this is for x. Okay. So writing this in a new slide, we have PV equals to 2 upon 3 n. N came from small n into v into half m v square average. Now you also know, say suppose this is a system. Now it is at rest. So the internal energy, if this is my reference point is 0. So the total internal energy is because of the motion of the particles, because of the random motion of the particles. So this gives this body a kinetic energy, and that kinetic energy, the total internal energy, is because of the movement of the particles, which is actually your total kinetic energy. So because it is just rest and we have taken the reference point over here, so there is no potential energy 0. All the energy, internal energy, is because of kinetic energy. So E equals to half m mass of one molecule into v square. But the total number of molecules that is present is n. So the total kinetic energy is n, total number of molecules into energy of one molecule, half m v square. So this gives you the total internal energy of the system. Therefore, my above equation is given by PV is equal to 2 by 3 into E. This is what this can be termed as, if you look closely, this can be derived from over here. Now, half mv square is the kinetic energy for one molecule. Now, if you're looking at the total kinetic energy, that is multiplied by n half mv square, and this term n into half mv square is over here. So PV equals to 2 by 3 into E. This is what we can write. And also we know initially in our calculation we had E, that is E is actually equal to 2 by 3 this is E. Now if you look at the previous slide, what we had was E is equal to 3 by 2 into Kb into Nt, where Kb is the Boltzmann's constant. So this is what energy was given to us as, because of Boltzmann's constant. This is what we had derived in our previous videos. So now if you compare this, say name this as equation A, name this as equation B, this as equation C. So if you compare these two equations, you have, if I take n below, E by n is nothing but your 3 by 2 into Kb into T. So finally what you have is E by n is nothing but your half m v square. Now E by n is half mv square. This is what E by n is equal to, half mv square. Now this is actually equal to 3 by 2 Kb into T. Kb into T, where Kb is the Boltzmann's constant. So this is the way we had derived. This is the relation between kinetic energy and temperature. So this is your temperature T and this is your kinetic energy E, the total kinetic energy. So E the final relation will be given as E is equal to N into 3 by 2 into Kb into temperature T. So this is the relation between E and T, and this is what we wanted. This is our derivation.